My name is Na Liu. I will start my presentation. This is outline of my talk. I was asked to cover some basics. So as you see from my outline, I will first give the students some overview in terms of the basics of DNA nanotechnology, plasmonics, chiral plasmonics as well. And then I will show you several examples about DNA-assembled plasmonic building blocks for different motion. And then in the end, I will also give you some perspective regarding the oligomerization of these DNA-assembled building blocks for collective motion. So I will start with the basics about DNA nanotechnology first. So if we take a look at a DNA molecule, you see it has two long polymer backbones made of sugars and phosphate groups. Nucleic bases A, T, C, and G, they are attached to the sugar part. So DNA is actually ideally suited to encode genetic information. So then the field started with the wish from Professor Nat Simon. So already back in 1982, he wanted to organize proteins using DNA to form three-dimensional lattices so that he could study these structures using X-ray crystallography. So after several decades, this field has enriched a lot. And as a matter of fact, the breakthrough, one of the breakthroughs came with the idea from Paul Rosamond. So he works in Caltech. In 2006, he came up with the idea called DNA origami. The basic of this concept is to fold DNA to create nanoscale shapes and patterns. I show you an animation in the following to give you the impression regarding how DNA strands can be organized to form really arbitrary 2D and 3-dimensional structures. So we start with a scaffold DNA molecule called M13. It looks like a loop. And then we add these pre-designed DNA shorter strands into the solution. So these shorter strands can find their ways to fold the scaffold DNA through DNA hybridization into 2D or 3D shapes. So this is a 2D rectangular shape. So origami is a Japanese word meaning paper folding. Therefore, the folded structure is often called DNA origami. The key to functionality is these capture strands that we can extend from the DNA origami template. So if we extend these capture strands away from the origami template, then imagine if I have functionalized nanoparticles, for instance, gold nanoparticles, silver nanoparticles, carbon nanotubes, molecules, proteins, aptamers, so on and so forth, then they can be attached very accurately at these capture strand sites with nanometer scale. So the important fact is that we can design DNA origami in 3 dimensions so that we can also make very arbitrary 3-dimensional origami structures. Hello?
Yes. Yes. We can hear you, but we cannot see you.
Sorry, I was offline.
Yes, just for a few seconds. Actually, we could hear you, but we did not see you. Yes.
Yes, I can hear you.
Yes, I can come. Yeah, yes, can you hear us or not? Actually, we can hear you. So. Elle écrit? Non?
Okay, she's back.
So, I'm sorry, it shows that the connection is really good. I don't know why I was kicked out from the line. I will just try again to share the screen.
Yeah, actually, Yes.
But you can switch off your camera, maybe, if you prefer.
Oh, I switch off my camera. Maybe that is better. Okay.
Yeah.
Okay.
I apologize.
Yes, me too. Okay.
So
Perfect.
Yeah, we see.
Yeah, it seems to work.
We see your screen.
okay. So then this is the basics about DNA nanotechnology. So next, I will also introduce to the students the basics of plasmonics. So when light interacts with a metallic nanoparticle, say a gold nanoparticle 100 nanometers in diameter, plasmons, which are correlated with the collective oscillations of electrons, can be excited. The resulting plasmonic resonance is highly dependent on the material of the particle itself, the neighboring environment, the geometry and shape of the particle. So then if for a spherical nanoparticle, then we can have the exact solution of the light scattering of light by such a spherical nanoparticle. So basically, we start from the Maxwell equation to result in the Helmholtz equation with appropriate boundary conditions. And then in the end, we can get the exact solution. So this is okay for the spherical nanoparticle. However, if we want to go to more complex geometries, for example, triangles with very sharp edges, nanostars, which are very good for SERS applications, so very complicated geometries, then likely we also have numerical treatment methods. For example, there are commercially available software like finite difference time domain, finite element method, boundary element method software to use. So in this lecture today, I'm not going to talk about the complicated derivation process. So rather, I want to give you some physical insight about the light-matter interaction. Especially, I want to give you the example when light interacts with a small nanoparticle in the quasi-static regime to see the insight. So the problem now we can nail down to the quasi-static approximation. So what does that mean? It means that if I have a small nanoparticle, I give the diameter, say the diameter is 2a or the radius is a, and then my operating wavelength is lambda. So the dimension of my nanoparticle is far smaller than the wavelength of the incoming light. So then in this regime, we can treat the entire problem with the quasi-static approximation, and we can use the Rayleigh theory of optical scattering. So here I have the say gold nanoparticle as an example, and then I say the dielectric constant of my nanoparticle is epsilon1, and then the neighboring environment is epsilon2. So then here E0 is my incoming light. So what I'm going to do is try to find out the field, electric fields inside the nanoparticle, which is called E1, and then the electric field E2 outside the metallic nanoparticle. So of course, they can be derived from the two scalar potentials, phi1 and phi2, respectively. So then the Helmholtz equation can be simplified to Laplace equations in source-free domains. So then we can add boundary conditions. For instance, phi1 should be equal to phi2. That means at the border of the nanoparticle, they should be the same. And then we also have the two equalities of the normal components of the displacement field as well as the tangential components of the electric field at the border. And then the fourth one is at the limit, so R, so that means the distance is in infinity, and then the field we have is only the external field. So if you are interested into the process, then I refer you to this book from Stephen Meyer called Plasmonics, Fundamentals and Applications. So then with the equation and the boundary conditions, I'm telling you that in the end, you can get the solutions. So phi 1 is the electric potential inside the sphere, and phi 2 is the electric potential outside the sphere. So then let's just leave phi 1 out for a moment. We take a close look at phi 2. So you'll see phi 2 consists of two components. So the first one is nothing but the external field contribution. So the second one is very interesting. So it looks complicated, but at this moment we can make several definitions so that we can make the solution which looks very meaningful. If we define the dipole moment P is equal to epsilon 2 times alpha times E0. So epsilon 2 is the the dielectric constant in the neighboring environment of my metallic nanoparticle. So epsilon 0 is my incoming light field. So alpha is defined as dipole polarizability. So alpha is equal to 4 pi a cube. So a is the diameter, the radius of my nanoparticle. And then I also have epsilon 1 minus epsilon 2 divided by epsilon 1 plus 2 epsilon 2. So epsilon 1 is the dielectric constant of my nanoparticle. So alpha is, in the sense, material dependent or material specific. So here, if I have these two parameters defined, the second term in my phi 2, this electric potential outside of my metallic nanoparticle, can be simplified into this form, which is in red. So here I have cosine theta divided by 4 pi epsilon 2 times r squared. And then here, this is my dipole moment. So at this step, this might already ring a bell in your head. So because maybe when you were a bachelor student, you have dealt already with this problem to calculate the potential at an arbitrary point next to an electric dipole. So the electric dipole consists of two charges, minus q and plus q, and they are displaced by a distance of d. So now if we calculate, for instance, at this point of interest, then here the potential at this point can be derived. Exactly, you see, if here P, this is the dipole moment, and that dipole moment is Q times D, and the potential at this position P can be written exactly as cosine theta over 4 pi epsilon 2 r squared times P. So P is the dipole moment. So if you compare these two cases, the top one and the bottom one, and this already gives you the insight. So in the quasi-static domain, when a metallic sphere, for instance, interacts with an incoming light, then the sphere in the static field is equivalent to an ideal dipole. So this is very insightful. That means when light interacts with such a metallic nanoparticle, when it is really teeny tiny, especially when compared to the dimension or the wavelength of my incoming light, then I can just treat this nanoparticle as an effective dipole. So then if we go further, we can also calculate the electric field inside the particle. So that means I just do the electric field, which is minus the gradient of the electric potential. And you see here, inside the metallic nanoparticle, the electric field is homogeneous. This is not surprising in this quasi-static domain. So then, which is more interesting is the field outside. We can get E2, which is minus the gradient of E phi 2. And the first one is the contribution from the external field, the incoming light. And then the second component is, of course, the scattered field from this electric dipole. In the sense or in conclusion, one can treat in this domain the metallic nanoparticle as an effective dipole. when it interacts with the incoming light. So then the resonance takes place when the Rayleigh condition is fulfilled. That means the particle polarizability will diverge. So the denominator is epsilon1 plus 2 epsilon 2. So that means this will go to 0. And then we get this Rayleigh condition, that is epsilon1, which is equal to minus 2 epsilon 2. So that means when light interacts with such a nanoparticle, then here at resonance, the electrons oscillate back and forth in the nanoparticle. So if here I give epsilon1, which is the dielectric constant of a metal, and I use the simplified Joule model, so that is 1 minus omega p square divided by omega square. So omega p here is plasma frequency. You have to be very clear about it. This is plasma frequency, not plasmon frequency. The plasma frequency is equal to n times E square divided by epsilon 0 times m. So n is the electron density and E is the charge. Epsilon 0 is the vacuum dielectric constant. So then in the end, for this spherical nanoparticle, we can get the resonance frequency, which is omega p divided by square root of 3. And just for your information, because of this Rayleigh condition, you see we can use the nanoparticle as a very good environment sensor for plasmonic sensing, because the resonance condition is highly dependent on the refractive index or the dielectric constant of your neighboring environment. Okay. So this is the introduction of the basics of plasmonics. So in summary, in the quasi-static domain, when our nanoparticles are really teeny tiny, much smaller than the wavelengths of light, we can treat them as effective dipoles. So now in the third section, I will introduce to you chiral plasmonics. After I have talked about basics of DNA nanotechnology and plasmonics. So this is a very extraordinary paper published already back in the year of 2011. So what you see is that the gold nanoparticles are organized in regular 2D lattices using DNA. So from the TEM, you don't see the DNA, but you do see gold nanoparticles. For a long time, gold nanoparticles have been used as image markers because of their high contrast from TEM microscopy. But imagine, even though you have built such very beautiful structures, if you just put these structures into a cuvette and then you measure their optical spectra, then it comes out that you just have some broadened spectra, nothing else. Not really so much information can be derived from this. Therefore, we ask ourselves, since we have gold nanoparticles and we can excite really nice plasmonic resonances, then can we utilize the plasmonic resonances as well? That means we utilize gold nanoparticles as the optical probes, not only as these simple imaging markers. This is one question. Another question is that, is it possible that we can even accurately discriminate the conformation changes in such ensemble structures? Because when we have ensemble structures in solution, they have all different orientations regarding the direction of light. Therefore, a lot of effects will be just smeared out. We need to take this into account. So that is question 2. The question 3 is that, is it possible that we can even use optical spectroscopy to resolve sequential nanoscale motion in real time? You know, several nanometers, so in nanoscale, such motions are really below the optical diffraction limit. And then the question is really whether we can use standard optical spectroscopy to distinguish such nanoscale motion. So with these questions in mind, we have to come up with the new idea to solve such issues. So we would like to use circular dichroism spectroscopy. And I will tell you why step by step. But I first need to tell you or introduce to you the terminology called chirality. So chirality, if we say an object is chiral, meaning its meaning is that the object cannot be superimposed onto its own mirror image. So for instance, in chemistry, we can find a lot of molecules, or DNA itself is chiral. Many proteins are chiral. And if you have not been very familiar with molecular chemistry, then you know snails. You also know our hands. Our left hand and right hand, they are chiral. So they cannot be superimposed on their own mirror images. So then in chemistry, so circular dichroism spectroscopy, or in a very simplified form, it is called CD spectroscopy. It is very well popular to be used to analyze conformation change of chiral molecules, or so to say, enantiomers. So what happens is that I put chiral molecules, enantiomers, left-handed molecules or right-handed molecules into a cuvette, and then I have the incident light. So then I measure the absorption difference when the chiral molecule interacts with left-handed and right-handed circularly polarized light. The resulting CD signal is very sensitive to the conformation change of such chiral molecules, and that is why CD spectroscopy is very, very suited or popular to analyze different enantiomers. You know, enantiomers is very, very important for medicine because different molecules which have different handedness, they might have entirely different biochemistry effects. So this is the information. So then indeed, in 2012, Anton Kuzik and Tim Little, as well as Seymour Fritz, they came up with the idea to utilize DNA origami as template to organize these gold nanoparticles in helical forms. So, you know, helix or spiral, they are chiral molecules in the sense that they have built artificial plasmonic chiral structures. So these gray bundles, they are DNA origami structures, and they are used as the templates. The gold nanoparticles, which are functionalized with different capture strands, they are assembled along the staircase fashion on the two origami bundles in the left-handed form as well as in the right-handed form. So then they, so here in the middle, you'll see the beautiful structures. They are really 3 dimensions. So then they measured the CD spectroscopy of these right-handed structures and left-handed structures. And here, another information I need to tell you, for natural molecules, say DNA or proteins, they have their chiral response mostly in the UV range. You see, if we have plasmonic nanoparticles, the CD response can be pushed all the way to the visible range, where the resonance of these nanoparticles takes place. So that in this case, it was around 524 nanometers. This is the first information. The second information is that here, unfortunately, because the gold nanoparticles are so small, they are as small as 10 nanometers, the CD response is very, very weak. So here, I think the data were quite noisy, and the authors had to smooth it. So then this gives us the opportunity that we have to look for another plasmonic system, which can have larger CD response. So then this was proposed by Lisa Mazan's group in Spain. They proposed this crossed finger configuration. Cross finger configuration is as follows. So instead of using spherical gold nanoparticles, which are quite small, then they say, how about we use 2 gold nanorods, and then we displace them along the Z direction. These 2 gold nanorods, they can also interact with each other. When light interacts with such cross-finger structures, plasmons can be excited in these 2 gold nanorods, and then they will work as 2 effective dipoles, and they interact with each other. And this is a chiral plasmonic structure. And in the end, we can also have CD spectra from the structure. And the CD response can be much, much stronger compared to the case of the spherical helices. So indeed, if we take a close look to understand the physical inside of such structure, so here, this is a cross-finger structure. So instead of they kind of cross along the central axis, they can also be stacked at their corners. So I like this nanolighter paper a lot. So I also refer you to read this paper to understand the plasmonic chiral effect of such cross-finger structures. But here I still will give you some explanation of the system. So this is the D enantiomer, or you can understand it by right-handed structure. And this is the enantiomer. This is the left-handed structure. So then these are enantiomers. So now I have this right-handed structure only, but I switch my light from right-handed circularly polarized to left-handed circularly polarized. So if we start with RCP, the field vector of the incoming light on the 2 nanorods will be in phase. You see these 2 arrows which represent these 2 dipole directions. So on the other hand, for LCP, the left-handed circularly polarized light, the field vectors on these 2 nanorods will be out of phase. So if you have learned molecular physics, you know, then when 2 atoms, they join together to form a molecule, then hybridization will take place. This is very similar to the case of the hybridization when 2 atoms join and mix to form a molecule. I have these 2 gold nanorods, which are 2 individual dipoles. Then I put them together in close proximity. Then light interacts with such a plasmonic chiral system. I can excite the anti-bonding mode, meaning the 2 dipoles, they oscillate in phase. And I can also excite the bonding mode, meaning the 2 dipoles, they oscillate out of phase. The anti-bonding mode lies at the higher level because here I have the same charge at this end, the same charge at this end, and they are repulsive. And this results in a higher energy level. On the other hand, I have the attractive force at the corner, for instance, and then this results in the bonding mode, which has the lower energy level. And this is called plasmohybridization. And this entire coupling effect can be explained by the Born-Kuhn model using 2 coupled harmonic oscillators. For instance, so here I use this one to represent the first top gold nanorod. And then I have this oscillator, which represent the bottom gold. So they are vertically displaced, but they are not alone. They are not independent. So rather, they are connected by another spring. They are connected by another spring, which represent the interaction between these two harmonic oscillators. So imagine if you have the coming light along this x direction. In this paper they define this as the y direction. So if I have the light polarized along y direction, then because of the interaction between these two harmonic oscillators, then the outcoming light will not only polarize along y direction, but rather it will also have component along the x direction due to the interaction between the two harmonic oscillators. Therefore, this results in the polarization rotation effect. So then after some effort using the Bronco model, one can derive the optical rotary dispersion, which is dependent or as a function of omega over 2c, and that is the real part of gamma. So gamma is equal to delta n. Delta n is the difference between the effective refractive indices of the right-handed light interacting with the object, and then the left-handed refractive index when the object interacts with the left-handed circularly polarized light. So the CD result is dependent on the imaginary part of gamma. And for your information, CD and optical rotary dispersion, these two terms, they are not independent. Rather, they are trimers chronic related. So if we plot them out, so this right one is the CD spectra, and then ORD is plotted in the blue line. So they are correlated. All right, so after we have obtained the insight about DNA technology, plasmonics, and slightly the chiral plasmonics, so in the following, I will show you several examples about the DNA assembled plasmonic building blocks for different motion. So this comes up with a key question as follows. So is it possible that we build DNA-based artificial nanosystems with tailored optical functionalities? And we actually first look into the living cell. So in living cells, there are many remarkable molecular motors. For instance, ATP synthesis, which can perform the rotation motion. And we also have linear motors, kinesin 1, which can walk along microtubules, and myosin kinesin 5, which can do the sliding motion. We were very inspired by such molecular motors, and then over the last 7 years, we have been building DNA-based artificial systems with optical responses, which can mimic such molecular motors. I will show you one by one. The first one we did was the dynamic system with rotation. So here, this was the work performed by my previous postdoc, Anton Kuzik. So what he did was he started with the chiral construction. On this slide, you see I have two chiral structures. The two gray bundles, they represent two origami bundles. And then the two bundles, they are connected through their hinge area. And then we assemble two gold nanorods, each on one origami bundle. The two bundles, they are not totally flexible, so rather they are connected at their hinge area using scaffold DNA. So we can build the left-handed version and right-handed version. And so then we can also change the angle between the two gold nanorods so that we can change the conformation of the nanosystem. Meanwhile, we can use CD spectroscopy to track the optical responses to retrieve how the plasmonic nanosystem has performed their nanoscale motion. So this is the DNA-controlled dynamic system. And this is the angle that I have been talking about. We would like to change the angle between the two gold nanorods. And I have, so we have also designed these two DNA locks, one on left side and the other one on the right side, the two locks can be opened and closed so that we can change the angle between the two golden nanorods and therefore the conformation of our plasmonic chiral system in real time. So before I show you the experimental result, I need to explain to you another term which we use to drive the system in a dynamic way. This is called toehold mediated strand displacement. So here I have 3 DNA strands in red, blue, and green. So initially, the blue strand is partially hybridized with the green strand. And then I add the red strand into the solution. So the red strand has the advantage to be fully hybridized with the green strand because these two strands, they have fully complementary DNA sequences in the sense that through a competition process, this blue strand can be displaced from its original position. And in the end, the two strands are fully hybridized. We will use this dynamic process to drive our plasmonic chiral system. So this is the operation schematic. So at this moment, we have left out the golden nanorods. We only show the conformation change of the template itself. So this is the DNA origami template. I have the two DNA strands at locks. And then we add the removal strand to initiate the first strand displacement reaction. So here, the double-stranded DNA on this arm will be displaced, and then we have this single-stranded DNA after the displacement. Now the two blue parts on the two arms can be used to do the hybridization. The structure is locked into the left-handed state. So next, if I add return strand through the second toehold mediated strand displacement reaction, this lock can be opened. Then my system can go back to the relaxed state. So similarly, we can also drive the system between the relaxed state to the right-handed state. This is the process. So you see, I add the driving strand into the solution, and then the plasmonic system is locked into the left-handed state. And next, I add the return strand. This lock will be opened, and then the system will go back to the relaxed state. So during the process, I can change the angle between the two gold nanoparticles in a very dynamic way. So these are the TEM images. On the left, you see the DNA origami frames, which look like crosses. And then on the right, you see how these gold nanorods are assembled on these origami templates. Then we did the CD spectroscopy. Maybe we take a look at the 3 representative CD spectra first. The red curve represents the left-handed CD spectra. The blue one represents the right-handed CD spectra. So here, this black one represents the relaxed state. So if we monitor the CD signal at a fixed wavelength around 750 nanometers, when we add the driving strands into the solution alternatively, then we can identify very well 3 different states, meaning when we add the driving strands into the solution, the system can be switched among left-handed state, relaxed state, and right-handed state. So we do see system degradation over time because we need to add these driving strands into the solution, and this introduces dilution effects. So therefore, we also came up with the concept to build all optically controlled system. Instead of using the DNA-driven process, we have designed a photoswitchable switch. So we have to utilize the Azobenzene photoisomerization. Just long story in short. So what we have done is we utilize this process. So in fact, Azobenzene has 2 forms. One is called trans-azobenzene and the other one is called cis-azobenzene, meaning when the molecule interacts with UV light, then the planar molecular structure will be transformed into this kind of twisted conformation. Then this twisted three-dimensional conformation can also be relaxed back to the trans-azobenzene conformation, and using visible light, the conformation change is on the order of 3.5 angstroms between these two states. Then what we want to do is we want to utilize the photoisomerization of azobenzene molecules so that we can utilize all optically controlled input to drive our plasmonic system. This is what we have done here. This is the azobenzene photoisomerization itself. Then we intercalate these azobenzene molecules in between the DNA bases so that originally here we have the DNA duplex. If we shine UV light, these azobenzene molecules, we will have the conformation change into this twisted three-dimensional form so that here these two DNA strands will dehybridized. Vice versa, if we shine visible light, these azobenzene molecules will return back to this linear form so that they can be intercalated in between the DNA bases again so that the two DNA strands can be hybridized. So now if I attach this azobenzene modified DNA duplex onto our plasmonic DNA structure, so this red piece represents this entire azobenzene modified DNA duplex. Meaning, if I shine UV light onto this structure, then my plasmonic structure will be opened because here this is light sensitive switch. If I shine visible light, and then here this lock will be relocked so that my plasmonic system will go back to the locked state. And these are the TEM images. If you check carefully, you can also take a look at this DNA lock in between these two origami bundles. And we have also done the reconstructed image from many of these TEM images, and the conformation between the two origami bundles in terms of the angle is 50 degrees because 50 degrees gives us the strongest CD response from our experimental parameters. So then in the experiment, what we have done is we have these plasmonic structures hosted by DNA origami template in a cuvette. We shine UV and visible light alternatively to erase and write the chiral conformation changes. And simultaneously, we utilize circularly polarized light to read the conformation changes optically in real time. So these are the experimental spectra for the relaxed state and the locked state. And we again will monitor the CD response at around 720 nanometers. And these are the experimental results here. You see in this case, when we shine a visible light and UV light alternatively, the CD response is oscillating between the two states without significant degradation anymore, because in this experiment, we don't use DNA strands as the driving fuel. Rather, we use all optical control. There is no waste included in the system. Therefore, the system becomes much more robust. Also, we can translate the molecular motion of azobenzene molecules into much larger conformation change translated by the origami template. So then the next is a little bit about the application of such dynamic plasmonic platform. So here I also have this slide to summarize the difference between antibody and aptamer. So everybody knows antibody, especially during this corona crisis, we really need the antibody. So anyway, antibody is normally these Y-shaped proteins, and then it is produced by our immune system. The production of such antibodies is quite expensive if we want to use it in the experiment. So alternatively, we can also design, so to say, the artificial antibodies, and they are called aptamers. They are artificial DNA or RNA structures. So they are nearly 10 times smaller. So that so here you see the comparison between the antibody and then the artificial antibody called aptamer. So this is much smaller than the real ones, and that means they are much better to access to cells, and they have many applications, and they can also readily produced by chemical synthesis much cheaper. So here then in this work, we have utilized aptamers. So on this platform, I again have these two gold nanorods, but I have this this origami template, which looks like a rectangle. And then I also have this origami bundle in gray. On the bundle, I have this gold nanorod. On the back surface of this origami, I have another gold nanorod. So along the two diagonal directions, I have two pairs of aptamers. So if you have if you are not familiar with aptamer and target regulations, it doesn't matter. So in a very simplified understanding, what you can understand is, for instance, this blue strand, this is an aptamer. Okay, these aptamers can be designed in a very specific and a very selective way so that they can grab or trap certain molecules. For example, this blue one that is designed to band or trap cocaine molecule. And then along the other side, we also have another aptamer. It is called ATP, split aptamer. It can be used to band ATP molecules. So ATP molecules, they are the energy currency in our living cells. So then in this experiment, you can understand that. So here I have these blue strands. When they are bent together, then they can trap cocaine molecules. Then along this direction, when they are bent along to this conformation, they can be used to band ATP molecules. So then that means I can use this Plasmonic chiral platform to do sensing. For instance, if I have cocaine molecules, then my Plasmonic system will be directed to right-handed configuration. While I have ATP molecules in the solution, then the system will be directed to the left-handed configuration. Then by reading the optical responses, I can determine what kind of molecules are in my solution and how much so the amount of molecules into the solution, in the sense that with this platform, we can do optical sensing of multiple target species using just one single plasmonic structure. So this is just some insight regarding the applications. So in fact, over the last several years, we have tried out many dynamic controls of these plasmonic platforms. I have introduced to you the DNA control, the light control. We have also actually made a pH control, thermal control of such plasmonic systems. And then I think I have 10 minutes left. So I actually have prepared many more slides, but I rather maybe finish this part. So this is a relatively recent piece of work. It is called a rotary plasmonic nanoclock. The thing is that you see for the previous presentation slides, I only show you the switch of our system between just several angles. Then the question is, if we want to imitate, for example, the full rotation of the ATP synthesis machine, then we need the rotation of our plasmonic system from 0 to 360 degrees. So then this is really the motivation. So my postdoc, Dr. Ling Xin, has designed this plasmonic nanoclock. We have this gold nanorod on top and then a second gold nanorod on the back surface. So here, the important thing is that we have this ring track. That means through the appropriate control, this gold nanoparticle on top can rotate against the bottom gold nanorod clockwise or counterclockwise from 0 to 360 degrees. I show you the design schematic. This is the ring track. We have 16 bending sites in 8 pairs. And here we have extended these black feet from the bundle, and the black feet can bend, for example, at this position at sites 1 and 1 prime. If we add the DNA driving strands into the solution, the 2 feet will be dissociated from position 1 and 1 prime, and then will bend to 2 and 2 prime. So then every time it can rotate by an angle of pi/8. If we do this continuously, the gold nanorod on top can rotate from 0 all the way to 2 pi. This experimental result shows you the counterclockwise route in red and then the clockwise route in black. You see at each angle, the 2 data points agree with each other very well, meaning the reversibility of the system is very good. Not only that, we also tried autonomous rotation, meaning we don't need to have the human intervention. We have instead the enzymatic reaction to drive the system to rotate in an autonomous way. It's really like autonomous driving. So of course, here we have the DNA enzyme strands in green color. So I don't want to go into the chemistry part. I just show you the basic idea. So what it does is that I have these DNA enzyme as feet in green color. Along the ring track, I have the purple strands. They are RNA strands. They are called substrates. So then here, what it does is that the DNA enzyme strand can cut the RNA strand so that it can initiate the rotation autonomously. I have the animation for you. So here, this is the this is the RNA, the DNA enzyme strand, and then the red, the blue one is the RNA substrate. So here I have this enzymatic core. Whenever it recognizes this RNA, the cutting position, then it will cut through in the presence of ions in the solution to cut or to break the RNA substrate, so that here this strand can walk along the track without turning back, because this is based on the burnt bridge mechanism. So I show you the animation. So this is the autonomous walking along this DNA track. So then if we have a ring track, that means we can initiate the autonomous rotation along this ring track, either clockwise or counterclockwise, very similar to the case, for instance, if you go to the airport, you see this antenna tower. The antenna can rotate against the stator, the tower, clockwise or back counterclockwise. So maybe in 4 minutes, I can also slightly show you, other than rotation, we have also tried, for instance, a walker. So that means the gold nanorod can walk along the origami template step by step, every time 7 nanometers ahead or backward. So this is the experimental result. So this is, we can already take a look. So what it does that we drive this Walker Gaussian nanorod from this side to the other side. And then in the meantime, we measure the CD response by monitoring the CD signal at around 680 nanometers. So we see that in real time, we have the CD signal changes. And for each step change, that corresponds to a 7 nanometer distance change in space. 7 nanometers is well below the optical diffraction limit. Just because of the very sensitive CD spectroscopy, we can even distinguish such 7 nanometer step change of the plasmonic Walker on the origami template, just using standard spectroscopy. And then when the system goes from position I to position 5, we can also drive the Walker in the backward direction, and one can immediately detect the CD increase, which goes back to the originally position 4, and so on and so forth. So again, we can also drive the system again towards the forward direction. So I actually have probably too many things to tell you, but I rather end up with this just a 3-dimensional version of the plasmonic Walker. So other than walking on just a planar platform, you can think of also to construct a 3-dimensional origami track. For instance, in this case, the Gaussian nanorod can walk on the 3-dimensional prism, and it starts from this side by crossing the peak over there, and then it goes to the other side, and then we can monitor the CD change in real time as well. And below you see the TEM images, which corresponds to the different stations. So this is the walking mode. So what I have not really enough time to cover is the sliding motion, but I think rather I stop it here just to give you the conclusion. So here, this is the conclusion. So in this talk, I try to cover some basics of DNA nanotechnology, the basics of plasmonics, and then I also showed you how to understand the chiral plasmonics by using the cross-finger configuration as an example. Then I talk about the example about rotation, and then the walking. I did not have time to cover the sliding motion, but maybe in the future, we could also have other opportunities to talk about more ideas and concepts. So with that, I would like to be really on time. And then thank you so much for listening. And also thank you so much for the invitation. I will be very happy to answer your questions. Thank you.